Hello children, welcome to Akshara 8 Foundation. So today we are going to start synopsis 2 in rotational mechanics. The rotational mechanics synopsis 1 we have completed up to the rotational angular kinematics, equations of angular kinematics we have completed and we have done the numericals there, okay. So now today we are going to understand, we are going to study the new concept that is about the torque. In the synopsis 2 we are going to learn about the torque there, okay. So torque is, what is the torque and where we can see in our daily life the torque, okay, what is the application of that and how to find out the torque, what is the formula of the torque, okay, that we are going to see there, okay. So now right up there, so this torque is also known as torque. So torque is also known as a moment of force, moment of force, okay. So what is the torque actually there? Torque, see here, so every day we will use our doors, no, okay, in the home we will use the doors, without doors cannot be, home will be there. So while opening and closing the door, okay, this torque will be active there. Simply we will apply the force perpendicularly on the handle of the door and it will be closed easily by a lesser effort, by lesser force, then immediately it will be closed and open the door there, okay, we can open the door. So then what is this torque there? Moment of force, what is the force we are applying and the door will be rotate, it will be rotate about the hinges, there are for the door there is a hinge will be there, no, like this, suppose it is a door there, okay. So here there are the hinges are there like this. Okay, this is open there. Now here at the hinges, so there are here the hinges will be there, like top and bottom it will be there, even it is in the middle also there. So now about this, this door will be open and closed there. Here the handle is there, and we will apply the force perpendicularly. Okay, we apply the force perpendicularly there. So like this. So and this is a, let us consider it is a perpendicular distance from this. About this axis, the door will be rotated there. About the axis, it is a door there, and the door will be open like this, no. Consider this is a hinges, okay, and the door will be open like this, okay. So it is the like this, the door will be open here, hinges, it will be open there and closed. So then whenever we apply the force perpendicular to this axis of rotation, so this distance is from the R is nothing but the distance of the perpendicular distance from the axis of rotation to the line of action of force where it is taking place there. Here the force is applying there, 90 degrees force we are applying there, then it will be rotated easily there. Even to open the cap of a bottles, even to open the tap, okay. So there also we will see there this torque. So it is an imaginary force which act on the objects when the force is acted at certain distance, okay. So then the body can be rotated about this axis there. So generally whenever we apply the force on a body, the body will be going in the direction of application of force, okay. So while it is coming to the rotatory motion, in the rotational motion, so we apply the force, then that force will be caused to rotate the body there, okay. So that imaginary force is said to be the torque or moment of force. Now simply it can be defined as, okay, it is defined as the cross product of, see we have learned in the vector chapter cross product of perpendicular distance, perpendicular distance from the axis of rotation, perpendicular distance from the axis of rotation, and the line of action of force acting on the line of action of force. Line of action of force acting on the body. Acting on the body. Acting on the body. So here this is a force. Here we apply the force perpendicularly. Even most of the cases we apply the perpendicularly or in different directions we will apply there. So then we will see there the line of action of force how it is taking there. Okay. So then here we will write their formula. Okay. The formula can be defined as here. This is a perpendicular distance. About this axis the door is rotating. The perpendicular distance up to the action of force and their line of action of the force, the product of line of action of force and the perpendicular distance is said to be the torque. So the torque can be here it can be written as torque is equals to perpendicular distance cross force. Okay. So this torque can be denoted by tau. It is denoted by the letter tau and perpendicular distance is r into cross here f bar. We know that this perpendicular distance is also vector and this force is also vector quantity. So that here this is it will be get a torque is also vector quantity. Torque is also vector quantity there. Okay. So it is also known as the moment of force. It is also known as moment of force. See, generally we have seen there in the vectors chapter, suppose one vector is acting here and another vector is acting like this. So let us consider is a A bar vector and B bar vector and angle between them it is theta. Then the cross product of this, so that can be written as here A bar cross B bar, we can write no, A bar cross B bar, A bar cross B bar. So we write here A bar cross B bar formula, what will get there here. So it is AB sin theta n cap, AB sin theta n cap from the vector code. Now here also we will get there R bar cross F bar, R bar cross F bar. So here we can write there RF sin theta. So that will be act perpendicularly the plane of these two, here A bar and B bar. So plane of these two vectors, the resultant vector, that is the cross product of the two vectors, it will be present there. Okay. So means this A bar cross B bar is perpendicular to B bar and A bar also. The plane of the two surfaces, plane of the two vectors, okay, it will perpendicularly. Then here tau bar is equals to R bar cross F bar, that means here RF sin theta will write there, okay. So now here if this is a perpendicular distance about this it is rotating, no, suppose. Then here we will apply the force, suppose it is the door and here we will apply the force there, okay. Then what is the line of force? Well, line of action of force, about the line of action of force, the perpendicular distance will consider there. So that perpendicular distance will be provide the torque. The torque will be always act here in this direction there. Torque will be act here in perpendicular to the plane of the two vectors. Okay. So the direction of this torque or direction of the moment of force, it can be find out by using the right hand thumb rule. Okay, right hand thumb rule. Okay, the direction of torque can be find out by using right hand thumb rule, because all the cross product is can be find out by using right hand thumb rule, no? So it is a cross product, so it is can be find out by right hand thumb rule. Right hand thumb rule. Okay. So what is the right hand thumb rule? If you place this one, suppose it is a right hand there, then the curled finger will show the direction of the plane of vectors, direction of the motion of the plane of vectors, and this one, the thumb will be indicates the direction of the torque there. Suppose here I said no, there are two vectors are there like this and like this. So this is a bar vector and this will be the B bar vector So now here it is moving like this. This is a bar cross B bar. It is a bar cross B bar. Now here, so if you move in clockwise direction, see if you move in clockwise direction, so if it is moving, it is a in clockwise direction. This is anti-clockwise direction, and it will be the clockwise direction there. Suppose the torque is moving in anti-clockwise direction, that can be taken positive there. So how it is positive? It is along the y-axis, no? It is along the y-axis there, and this one along z-axis and x-axis will be there. So if the torque is moving, means the plane of the two vectors are along the curled finger direction there. The direction, this curled finger of a right hand will give the direction of the rotation of the curled with these two vectors, and the thumb will be indicates the direction of the torque there. Means the plane of rotation of the perpendicular distance and the force acting on the body. It can be given by the direction of this curled finger. If it is moving anti-clockwise direction there, so the torque can be taken positive. Torque will be positive when the plane of R and F are in anti-clockwise direction there. Anti-clockwise direction. Anti-clockwise direction. Okay, and T here, this T can be taken negative there. It is clockwise direction. Whenever it is moving in clockwise direction. Suppose let us see here. This is the right hand and it is moving in this is a clockwise direction now, okay, towards right side. Then if it is a clockwise direction, then the thumb will be indicates downwards. It is moving towards the torque is, it is along the negative direction there. So here it can be taken negative there, negative y-axis there, negative y-axis. So here we can write there, the torque will be the negative when the plane of R bar and F bar in clockwise direction, in clockwise direction. Okay, so that is like that. The torque can be, direction of the torque can be taken, and here the torque, the formula of torque we have written there. Tau bar is equals to R bar cross F bar, and here this also can be equated as RF sin theta. And here the SI unit. What is the SI unit of this torque? SI unit of torque. SI unit of torque is, here the perpendicular distance is, it is measured in meters and the force is in newtons. So we can write here Newton meter. So Newton meter will be the dimensional formula. It is the SI unit of the torque. Then what is the dimensional formula? Dimensional formula can be written as here. Dimensional formula of this torque. Dimensional formula of torque. So dimensional formula of torque is Newton. Newton means m power 1, L power 1, T power minus 2, and here m is there. So we will get here m power 1, L power 1, and here L is there. So L power 2 will become, and here T power minus 2. So the dimensional formula of the torque is also equal to the dimensional formula of the energy. Energy also same dimensional formula, same SI unit now. Okay. So this is about the torque. Understood now? Torque is nothing but the moment of force by which the body can be rotated. Okay. The cause of action of rotation is done by using this torque there. So torque will rotate the body. Okay. So that is called, that moment of force is called the torque. Okay. Torque is an imaginary vector which acting there on the body plane perpendicular to the two vectors, that is a square, that is the perpendicular distance, where perpendicular distance and the force of line of action of force. Okay, it is about the torque there. So now we will see their next concept of couple. So what is a couple there? couple acting on the objects there. So couple is nothing but it is the torque exerted on a rotating body, torque exhibits on a rotating body. So when equal and opposite forces are acting on the body there, okay, equal in magnitude, it is in opposite directions. If the two forces are acting on the body, then this couple will be exist there, means so there will be the two torques will be exist there. So from about the line of about the rotation, about the axis of rotation, there are two forces will be act there equal in magnitude, but they are in the opposite direction there. Suppose let us see there, we are rotating the tap, okay, or closing the tap or opening the tap there. So when we are open there, we will use our fingers, two fingers will be, two middle finger and the first finger will be moves clockwise direction, and this one will be the, so this is another finger, the right finger also it is moving in, okay, one is moving right side and another one will be moving in left side there, okay. So then here two forces will apply the same force by using these three fingers. So then the body can be rotate easily, it can be open and it can be closed there. Even we can close also, we will apply the force there. To open it, we will apply in opposite direction, in anti-clockwise direction. These two forces will be act in anti-clockwise direction. Even though it is acting in anti-clockwise direction, then two forces equal in magnitude, but they are in opposite direction, they will be act there, so that the couple will be takes place there. Okay. So suppose if you take here a tap is there, and this is the tap, and we'll apply here to rotate this one, or in the park there is a crowbar, there is a play item will be there, no? The children will be sit here and it will be move about this, up and down it will move there. So one children will be applies here downwards and other will be go upwards there. Okay. So here the force, and here about this it will be rotated there, about this it will be oscillate like this, about this it will be oscillate. So one time it will be comes here and other time will be comes here, and it will be like that, it will be keep on oscillate there. So this is a force, is same force, equal force, but that is in opposite direction it will be applied there, so that this body can be moved there, even the cap also. So for a bottle there, okay, there is a cap will be there, no? This cap is also, it will be opened easily. So for the cap, okay, so we'll apply the force here, we'll apply the force like this, and we'll apply the force here like this there, and it is rotating about this axis, no, about this axis. So it will be rotated about this axis, and these forces are equal, and here the distance will be there, perpendicular distance from here to here there. Then there is a torque will be act there. Torque tau is equals to, we can write here, what can we write there? So F bar into here, so R2 bar minus R1 bar, R2 bar minus R1 bar we can add there. So the distance is R1 and the distance is R2 we can add there. Here tau is equals to, we can add here, here. So R bar cross F bar. So first we should write there here R bar cross. So here we should write R2 bar minus R1 bar cross. Here we should write there F bar. So this is a formula of couple acting there. So that is also it will be given. The couple is also, it is nothing but the torque acting on the same and same magnitude of torque and in opposite direction if it is act there, then that is called the couple. So then here we can add there R bar cross F bar. So this is the couple acting on the body. So this couple is also have the same SI unit and dimension formula as the torque there. Okay. So equal and opposite torque will be takes place about the axis of rotation. So then that is called the couple acting on the body there. So due to that couple, the body can be rotated easily. So we can open the bottle cap of a bottle, or open a top or close a top there, or we can open the door also, about the door. Okay, opening and closing of the door. This is about the couple. So couple is nothing but the square of the perpendicular, it is the perpendicular distance. So perpendicular distance about the axis of rotation, and the force of action of line of action of force equal, and it is equal in magnitude but is acting in opposite direction. So that is said to be the couple. Okay. So now next one we are going to see here the equilibrium of a body there, equilibrium of a body. So equilibrium of a body, equilibrium of a body there. So here if a body is in equilibrium means the body is at rest, or it may be that uniform motion. If sum of all the forces it is 0, then we can say the body is in equilibrium there. Even if a body is means linear momentum is constant there, then we can say, so linear momentum is constant before and after, then we can say the body it is maybe in the equilibrium there. See here in the rotational mechanics, equilibrium is nothing but the angular momentum will be constant there when there is no external torque acting there. So the angular momentum will be remains constant. So then before and after the action, the angular momentum will be constant there. So then the body is said to be in the equilibrium position there, equilibrium position. So here if external tau external is equal to 0, tau external 0, then we will get there dl by dt, dl by dt also it will become 0 there. So this will get there. So from the Newton's second law, tau is directly proportional to rate of change of angular momentum is directly proportional to the external torque acting on the body there. From that so dl by dt also it is equal to 0 there. Now dl is equal to, it will become 0. dl is 0 means what there? L2 minus L1 is equals to 0 we can add there. Now L1 is equals to L2 we can add there. L1 is equals to L2. L1 is equals to L2 we can add there. L1 is equals to L2 we can add there. Okay. So then in this condition the body is said to be the in the state of equilibrium there, in the state of equilibrium. Okay. Suppose then if a body is rotating, here the linear momentum is will be constant there. Linear momentum will be here, sorry, angular momentum will be constant there. Okay. Whenever there is no external torque, whenever there is no external torque, then the body will be linear momentum and angular momentum will be constant. Then we can say that the body will be in the equilibrium state. The body is said to be in the equilibrium state there. So or we can say here moment of force, moment of force or torque will be is equal. Torque is equal. Sum of the torques is equal there. So then all that also we can say there equilibrium state of a body we can say. So there are the simple machines we have learned there, the principle of momentum. So principle of momentum is nothing but torque acting on a body before and after it will be, so means external torque will be equal to 0. When the external torque is 0, then external torque is 0 means, so the sum of the moment of the force acting on the body is 0 means here the torque is 0 there, torque acting on the body is 0 there. So then the body is said to be in the equilibrium position, the body is said to be in the equilibrium position there. Suppose in the simple machines we have learned there are different types of levers. So lever is a simple machine which has a load and fulcrum and effort. Okay. So by the simple application of effort, then if it do their greater work, then it is said to be the simple machine. No? There are different types of levers. No? So first lever, if you say there crowbar like a, so if you take a crowbar like this and it will be lifts the load there. So here we will apply the effort and here fulcrum and this will be the load. It is the fulcrum and load. Okay. Or we can say the seizure. So seizure will be there, no? Okay, load will be here and effort will be here there and this is a fulcrum is there. So here we will apply the effort force and fulcrum is there, load is there. This is a first case lever, no? Okay, first class lever. So in this here it is a effort there, means the fulcrum is in between now load and effort. There is it is said to be the first class lever, no? Then here the principle of momentum we can apply here, torque we can apply there. Here we apply the effort is nothing but it is a force, perpendicular force, and the distance between the fulcrum to the effort is said to be the effort arm, and the distance between the load and the fulcrum is said to be the load arm. Okay. So now the principle of momentum, it is nothing but load into load arm. The total torque acting on the body is said to be 0 there. Okay. Then in that case, load into load arm will be equal to the effort into effort arm we can add there, effort into effort arm. effort into effort arm. Effort arm is denoted by EA, effort arm, and effort is the E there. And your load, L, capital L, and load arm will be the LA. Okay. So now from this, we can write there like this. Do the cross multiplication here. Load by effort is equals to effort arm divided by load arm. Effort arm divided by load arm. This ratio is called the mechanical advantage. This ratio is called a mechanical advantage. The ratio is called the mechanical advantage. By using this mechanical advantage, so if the mechanical advantage is good for a lever, then we can say that is a good lever which will be work efficient for less effort. It will be do the work more. So then that will be treated that like that. Simple machines have the good mechanical advantage. That levers can be possible to take there. We will take that. If the mechanical advantage of a machine is good, then we can we will be choose that levers to our applications. Okay. So now this is about the equilibrium of body and the different types of in the first class lever we have seen there principle of momentum. In the principle of moment we have seen this mechanical advantage and the principle of momentum we have seen there principle of moment. So principle of moment is what there. See here the total momentum acting on the body is said to be 0 there. So then we can say the total momentum is acting, total moment, not momentum, total moment acting on the body is 0. So from that we will get this mechanical advantage equation. So here up to here this is the explanation of the concept in this synopsis 2. Okay. So in the next class we are going to see there conceptual based questions and the numericals. Okay. Thank you children. Have a nice day.